range of descriptive statistics that are based on simple distances. So the G function is simple cumulative distances to nearest events. The F is same thing, but from reference points. It's called the empty space function. And then the J function combines the two. And the advantage of that is that for complete spatial randomness, it's a constant. There is no distance in there anymore. And we can start making a connection between the value of the J function and some parameters of some spatial point processes, which can help us in the estimation later on. As I said, these are all based on distances, or the ones that we saw previously are based on the first moment of a point pattern. Think of a point pattern as something that is generated by a distribution, and we're interested in characterizing that distribution. So to characterize a distribution, the mean is not sufficient. Even for a Gaussian distribution, which is the most regular of them all, we need to have the first and the second moment. We need to have a mean and a variance. With those two, we can fully characterize a normal distribution. So we'll move along similar ways and try to find the counterparts of this for a point pattern to be able to characterize what the process is that generated the spatial pattern, to characterize the distribution, if you wish. And one step towards this is this K function, which is probably the most famous characteristic of point patterns. And as we'll see in a moment, or I should say, as we see shortly, the K function deals with the second order. But just to recap, the intent, and put it a little more formally than we've done up to now, the intensity function is something, it's an abstraction. I mean, our estimate of it is very simple. We count the number of points and divide it by the area. But that's just an estimate. That's not good enough to characterize a spatial process, because the spatial process is about the probabilities of getting an event in any particular location. So that's not just the number of events in a particular area, which is what we can get from a Poisson distribution, but it's also where they are. This is what it makes it a spatial distribution, a spatial pattern. Okay? And to get to that, we have to go through some mathematical abstraction where we basically think of the area as shrinking until it becomes very, very small, and the number of points in that extremely small area is what we call intensity of the process. Okay, so this is an abstraction. If you haven't done limits and derivatives and integrals for a while, this may be a little rusty in this. It's just a way to think about the process. It's a continuous process, something that moves over the whole space and defines probabilities for each possible location of getting an event there. That's really what we're after. Okay? Now, to get to that, we'll have to derive, find, estimate these characteristics from the points that we actually observe. So we can't work with infinitesimally small areas. It doesn't work that way. So we take proxies. We take like our quadrats, which are squares, or we take the whole area, a convex hull, count the number of points, divide them by the area. That's an estimate. That's not the actual parameter. The actual parameter, or the function, is something that should be defined for every location x. Now, the easiest way to define that is by saying it doesn't change. Okay? It doesn't change with location. In other words, lambda for location x is simply a constant lambda. And that is one of the characteristics, not the only one of the characteristics of a stationary process. So we'll talk more about stationarity when we get into the geostatistics. It's basically a requirement of equilibrium. And we need that because we only have, as I said previously, one data point. The pattern is a data point. It's not the number of events we have on our map. That's not the number of observations. There's one observation, the map. And so in order to cheat and turn this one observation into multiple observations, we have to go into some mathematical construction that says, well, things actually don't change. So it doesn't really matter whether we see this map or another one or 20 other ones or 100 other ones. They're all basically the same. And so what this is about is making more formal what basically the same means. And one way to do this is to characterize the distribution by its moments, like the mean, variance, and so on, and putting constraints on those moments. One constraint we can put is, say, the intensity is the same everywhere. So, in other words, if we want to estimate the intensity, since it is the same everywhere, it doesn't really matter where we get the estimate, or whether we get the estimate from a small area or a large area. It should be the same. That's why we have to impose these assumptions. Now, not all processes are stationary. We saw these Poisson cluster processes or heterogeneous Poisson processes. They are not stationary. In fact, we simulated some where the lambda x was, in fact, a random variable itself. So it changed randomly over space. Then you don't have stationarity. So stationarity is a special case that we'll always use as a frame of reference, as a benchmark. We will compare other situations to the stationarity one, First order moment is the counterpart of the mean, that's the intensity. Now what's the second order moment? The second order moment is the counterpart of a variance and a covariance. Now, covariance, why? Because we have possibly clustering and inhibition, which means there is an interaction between those points and their locations. So when you get a point in one location, the probability that you get another point in a nearby location is affected by that. So when that is the case, then we need more than just the variance, we also need the covariance. And so what is a covariance for a point path? What is a correlation between 2 points? That's not how it works. So the way we think about this is as what we call a cross-product statistic. A covariance between 2 random variables is computed from the product of the random variables. You multiply them with each other. So we'll be multiplying things. What we will be multiplying are 2 areas that in the limit become infinitesimally small, very, very small. So we'll take the number of points in one area, and we'll take the number of points in another area, and we multiply that by each other and divide it by the product of the 2 areas, and we'll make these 2 areas shrink as small as we can make them. The number that comes out of that is some measure of correlation between the number of points in each of these areas. If there is no correlation between them, it should follow a certain pattern. If there is correlation, it will be different. This is something that, again, we would like to estimate from the data. The intensity was easy. You just take an area, count the number of points, divide by the area, of the region. This is not that straightforward because we have to take 2 areas and somehow take the number of points in each of these and divide by the area and then multiply them together. So that's a little more difficult to grasp. But if you think of it as a counterpart of a correlation, are 2 densities correlated or not? That's really how one can think about this. And so what we want to find out is, by taking an empirical measure that is a counterpart of this, we will be able to say whether the pattern that we're studying has a correlation structure or not. And why is this important? Well, if the points are clustered, then 2 nearby areas will have more points in them than would be the case randomly, if you take 2 areas that are close together. If the point is regular, then they will have fewer points in them than they would under regular. path, under a random path. So that, again, is the point of reference. So formally, it's expressed here in the slide. We call this lambda 2 for two locations, x and y. And it's the limit as the areas become very, very small of this expected number of points in the area divided by the product of the area. So the expected product of the number of points in the area divided by the product of the area. Now we have different kinds of processes. One of them is this reference of a stationary process. For a stationary process, we don't want this moment to change. So we want this moment only to depend on how far the two little areas are from each other, not where they are on the map. So if you have, say, two areas that are 2 miles away from each other, and you compute the expected, on average, how many points there are in each of them and multiply that with each other, whether you do this in the northern part of the map or in the southern part of the map, it should be the same. The only thing that matters is the 2 miles. Isotropic processes, direction doesn't matter either. So isotropic, it's only distance matters. So it's not 2 miles and 45 degrees versus 2 miles and 90 degrees. They might be different. When it's isotropic, then they're all the same. So the only thing that matters is the distance. So this simplifies then, rather than having to specify the location of the first point and the location of the second point, all we need to know is how far they are apart. So this becomes expressed in terms of the parameter, in this example, t, which is simply the distance between the 2 points. And we'll see that again next week when we get into geostatistics. Isotropic processes, distance is the only thing that matters. Absolute location does not matter and cannot matter. Now, again, this is something you need to check. It's an assumption. It's not necessarily the case. It could be that the correlation structure among the points, between the points, changes in different subsets of the data. That if you have highly heterogeneous processes, it could be that in part, like, murders, Bill wants dead people. In certain areas of the city, there could be many more than in other areas of the city because it's a different process. Urban crime in certain areas of the city may be following a particular process, say it's gang-driven. And in the rest of the city, it's nothing to do with gangs. It's something to do with, say, domestic violence. So those are two different processes. And so then, in that case, you would not have stationarity. You would have different correlation structures, different second moments. Okay. So now, this thing is nice in theory, and we can go a little further. And just as we have joint distributions and conditional distributions, we can think about the conditional intensity. See, the previous one was the joint intensity. You multiply the two together. Conditional intensity is saying, what if I have an event here, and I know that? It's conditioned on the fact that I know that. How does this affect this product with the intensities between my point here and any other point? So that, just think of it as a counterpart between a joint density and a conditional density. This is the joint, the product, the lambda 2 for both x and y. This is the conditional, given that y is there is an event at y, and the result of this is the ratio of the joint to what we call the marginal, which is the simple intensity that we started in. So this is a second order moment, the numerator is. The denominator is a first order moment, is an intensity. Okay. For stationary processes, this is lambda. We already saw that, so this simplifies. Now, why is this important? And there's a lot of mathematical detail here. It's important because this gives us the connection to this k function that we still haven't talked about. Okay. So what is the k function? At first sight, you wonder how anybody ever came up with this. because it doesn't make any sense. It's the ratio of the expected number of events within a distance h from any arbitrary event to the intensity of the process. The reason this is done is to scale. You'll see later why. It's just this lambda is in there to make things more tractable. Now, at first sight, this is completely counterintuitive. What we'll see in a few minutes is that this actually connects to this second order moment. And remember what I said. Ideally, we'd like to estimate the second order moment, just like we like to estimate a variance and a correlation. And how are we going to do this when we have to think about areas, two areas with points in them that shrink and that we have to multiply together? There's no practical way of doing this. Well, this is the catch. This can be estimated. Why? Well, anytime you see this, E, which means expected value, expected values are estimated by averages. And everybody knows how to do averages. Okay, you just do things a lot of times and divide it by the number of times you do it. This is also the power of simulation. Simulation estimators use this, because if you can generate this many, many times, and you can take an average of it, then you have an estimate of the expected value. Anytime you see this, and this is in general, anytime you see this expected value in an expression, you have to think averages. Okay. So averages of what? Average of the expected, well, the expected is the average, the number of events within a distance h of an arbitrary event. Now, think about this. How would we calculate this? How would we estimate this? Arbitrary event is any point in the pattern. Distance, we know how to calculate distances. So we take a point, we draw a circle around it, right? Count how many points are in it. Do this for all the points and average it, and we're in business. Okay. So that's the power of the k function. You can do this for any h you want. For any distance you pick, you just draw the circles, count how many points are in the circle, and average it. And that gives you an estimate of this part. Now the other part, we already know how to estimate. The intensity, we take our region, our convex hull, our bounding box, count the number of points, and divide it by the area. So each of these, we know how to get an estimate for. Now the next step is to connect this thing, this k function, to the actual parameter of the process, which is the second order moment. And in the literature, the k function is called the reduced second order moment, because it's not actually the second order moment, it's connected to it. Okay. And this is my favorite slide. I actually had to go back to my daughter's high school textbooks to refresh my memory to make sure that it's right. I know you guys all love this stuff, right? What does this do? Any volunteers? It's basically counting, but for infinitesimally very, very small pieces. And the integral sign is nothing but an infinite sum. And so what you're doing is, for all possible circles, you count how many points are in those circles. And that is basically what is going on here. Now, this is the key. This is what we just saw in 2 slides ago. This is the conditional intensity. This is given that there is a point in this location, what is the intensity of points in a neighboring area? So given that intensity, if you integrate this out over all possible circles of all possible radii, then you in fact get the expected number of events within radius h from any arbitrary event. So this is nothing but this averaging that we just talked about, but put formally in terms of a characteristic of the process, which is the conditional intensity. And then we know that the conditional intensity is related to the second order intensity, and then the hocus pocus begins, and at the end of the day we're in business. This is the K function. It relates to the second order moment, actually to an integral of the second order moment. And it's scaled by this 2 pi lambda, 1 over lambda squared. You know, if you're into integrals, this all follows naturally. If you're not, it doesn't follow at all. Just take my word for it, okay? It is correct. Basically what we're doing is formally working out what these averages are in function of a continuous characteristic of the process. Anytime you say continuous, you say integrals, you say derivatives. It's the continuity that drives all this thing. If you don't have continuity, you can't do this. You have to add them up. You have to count them. So in practice, that's how we do it. In practice, unless all you have to do is proving things, you don't actually write this out like this. If you want to get a number for an integral, you have to count. And what you do is you make it a discrete problem. Rather than having it as a continuous problem, you take a bunch of tiny little intervals and just count what happens in those intervals. And that's, in fact, how we would do this in practice. The importance is that we have a connection between something, this kh, that we can easily estimate. We just saw how to do it. We take an average of these number of points within a given distance divided by the intensity, and this thing which is a bear to estimate. But the advantage is that this is actually a theoretical characteristic of the process. So with a little bit of integral hocus pocus, you flip this around, and then you find that this second order moment is in fact related to the derivative of the K function. If you've never done this, it's crazy, but you see this. We have this here, we have the lambda, this one moves over there, so that's the square. Then we integrate this out, it's up to a distance t, it becomes a constant, that's where this h comes from. And then, because you take a derivative on both sides, you get the derivative of the K function. That's as far as I'm willing to go. I can write it out for you, but I don't think it matters. The main thing is that you know that there's a connection between the two. So the K function is related to an integral, a summation of the second order moment. The second order moment is related to a derivative, the change in the K function. So summation is adding up, derivative is change in the K function by distance. So how does my K function change as I increase the distance? Since we can estimate the K function, we can figure out how it changes as h changes, and so we can estimate the second order moment. And now we can have a first order moment and a second order moment. That gets us a little closer to trying to figure out what is the actual distribution of the point pattern process. And that's the main power of the K function. As always, we want to know what is the K function for complete spatial randomness, and that actually turns out to be pretty straightforward because we know that the intensity is lambda. We just saw that the second order moment for a Poisson process is just like for a regular, well, I won't go there. It's lambda squared, and then we just plug this into the expression that we just looked at with the integral. Integral of a constant is about the easiest integral you can have. So that's where this h comes from, h squared. The 2, it's 1 over 2, that cancels out. the lambda squared cancels out with this lambda squared. So we end up with something which does not have the intensity parameter in it anymore. It's very important. You know, when you want these things, these functions, you don't want to have any parameters in there. There's no parameters in here. Pi is a constant, and h is the distance. So for every distance, we can plot what the k function would be for a completely spatially random process. Namely, it is a quadratic function in the distance. As the distance increases, this function increases. So now what we want to be able to do is compare an actual empirical estimated k function to this theoretical value. How do we estimate the k? We already talked about this. It's pretty straightforward. Averages. So expected events within a distance is the average of the number of events within that distance. So for each of the events in the data set, for a given distance, we look at how many other events are within that distance, and then we divide this over by the number of points in the pattern. That gives us the average for that particular distance. So for each distance, we get this average, and then we can plot it. So you take 1 mile, 2 miles, 3 miles, you compute it, and you plot it. The more distances you take, the smoother your curve will be, or the more jagged your curve will be, the more points you will have to get the estimate with. Same problem as before. As we get to the edges, we don't actually know how many points are within the given distance. Because some of these points are in our bounding box, some of them may be outside. So there's a whole literature of edge corrections, and I just keep it very simple here. Say proportion of the circle that is inside versus not inside. And so that's how you correct. You can also do it by area. There's a number of different ways that have been suggested. The bottom line is that you have to downweigh the evidence given by the points closer to the edge of your pattern. Because the closer they get to the edge, and especially for larger distances, you know, say your bounding box is only 5 miles squared. As you get closer to 5 miles, a lot of these points will have a circle that goes way outside the bounding box. And you have no idea what is going on in there because you don't have any observations. So when that's the case, you actually downgrade that information. So you take, instead of a straight average, counting every point equally, you have a weighted average. And you downweight the points that have a lot of edge effects. They don't contribute as much to your average. And so you can see, or maybe not, but you'll see it in a minute, as these distances get larger, we have greater and greater uncertainty about the actual estimates, because more and more of our potential neighbors might be outside the bounding box. So as the distance becomes larger, the estimate of the k function becomes less and less reliable. Or translated, the variance of the estimated k function increases with the distance for which we calculate. And you can just think of it as a box for which you need to calculate averages. As you get larger and larger distances, that box becomes thinner and thinner with reliable distance pairs, reliable circles. So then you get more and more unreliability, which gives you greater and greater uncertainty, which is greater and greater variance. That's basically what's going on. But the principle is very simple. It's averages. Yeah.
A question about edge effects. Is the reason why we downgrade the edge effect because we're treating the area that we're analyzing as a sample of the larger population?
The reason is that we're constructing an estimate, and you know, when you take an average for a given distance, say you have 50 points and you take 1 mile. So for each of the 50 points, you count how many events are within 1 mile from that point.
Right, and we assume the process is continuous beyond that space.
Yeah.
Okay.
So what you have to, well, you can assume that the process replicates itself outside the bounding box, and then based on that, you can make an edge correction. That's why, you know, I have it generically, I haven't put any specific formula in this expression. There's many different edge corrections. The basic idea is that because we get close to the edge, and because we don't really know what happens outside the box, those estimates are not as good as the ones where we do know how many points are in the circle.
What if we do know there's nothing outside the box, no edge correction?
No edge correction.
Okay.
Okay, let's leave it at this for now, take a little break, and then I'll give you some examples after the break.
Pause. Pause. Yeah.
Felicito por el premio.
Gracias. ¿Viste la?
Yeah.
And I didn't explain it, but it's given as like a block on the street. So like for any given point, any one of the blocks is going to be, have to be randomized or whatever. So like it's 73 block or Sheffield, and you just have to have that. It could be like east or west, either axis, but it's only one that has to be randomized. So
Okay, you don't have multiple points on the same block?
oh, absolutely. I mean, there certainly will be more than one on the same block. I will do the randomization, but it should make it fairly trivial to do it. It's only one axis.
Okay.
And not to worry. So.
But you still need an X and a Y, right?
Right. Well, that's what I'm saying. Is like when it gives.
When you said integer, that's
whichever.
what I got pulled up.
Oh, right. Well, no, yeah. I didn't like the idea of using coordinates. These things. It was going to like add false clustering, I guess. But the streets, I don't see any reason like the street, it's whatever position it is on the Chicago grid. Are you familiar with the Chicago grid system at all? It's
Grid system?
the grid system. It just,
I know the street patterns.
I mean, it's right. Well, each street just is given a number, like and it just goes like up to like 4,000 north, 6,000 south, like out west, or whatever. Each bridge is an X, Y, but like each street, a street has is on I got 100 assigned like a 100, 4,300 block. It associates to each a certain street. But anyway, each street is precise, like it's actually at that point. So I don't see any reason to randomize that. So just for each point, I'll randomize. If it's fine to be in a certain block, given the street will be precise, and then I'll 0 to 100 for the last part.
Okay,
The
in the
address.
box.
Right, but that'll lead to some sort of like a method pattern still. That should be that should be normalized. If I do an intensity surface and they're both in the same network, and then subtract it out.
Well, I know, but I mean it's realistic. It's usually more than yeah, 4 years.
What's that? Yeah.
I think I wouldn't worry too much. I think they'll tell you if you're doing it right. They'll tell you that you're
R is always the object oriented.
I did this one last year.
We'll talk about it on Thursday. Okay. Any more questions about this material? The assignment type questions we can deal with on Thursday. Okay, if you have, or if I'm done early, then we have a little extra time, then I can talk about that. Aaron?
I had one following up on Bill's question about taking the topography into account as you're drawing your circles. Let's say you have, like maybe for the purpose of illustration, you have an island. So there's a lot of water, and your events near the boundary are, even if, let's say, we don't take edge effects into account because we know there's no event in the water. But if we draw circles, you know, the circles that capture the events near the boundaries of the island are going to have fewer points in them than the ones in the center. So you have like a precision variance between these two. And then how do you account for that if, you know, edge effects aren't the answer for this issue?
Well, that's the WIJ is generically is a weighted averaging. So you downweight the ones where you have less precision, if that is the idea. In the boundary, in the edge effects, it's clear what the less precision is due to,
Yeah.
especially if it's, you know, a uniform plane without features. Once you have features, then things get more complicated.
Right, right,
Julie just mentioned something, topography, is there a Z in our point?
There can be, but I'm not going there,
Okay,
okay? I'm keeping it flat.
so all intents purposes, all point patterns are flat?
No,
No.
all the ones that I talk about here are flat. There are 3D point pattern, there is 3D point pattern analysis. In fact, in medical applications, this is, you know, detecting tumors, that's all 3D.
That's another class.
That's a totally other class, yeah. Then you have to know how these integrals work.
Right.
Okay, let me start this off again. So, we have an estimate of the K function, and we know what the K function looks like theoretically, so now we can apply this to actual data sets. This first slide shows the K function with 3 different edge corrections. So this is not the envelope, okay? This is the dark blue one, nice parabola. It's pi, which is just a scaling factor, and this increases with h squared. Okay. Then these are 3 different types of corrections. The one that I just talked about is using the circle idea. So it's basically you take the share of the circle that is inside the box versus the total circle. The green one is using the buffer zone. So it's the same idea. You shrink the actual data set and keep a buffer at the edge. And then this red one is the one that uses the flipping of the torus approach. So these, you see, in fact, it doesn't make a lot of difference in the smaller distances, but as you get into the larger distances, as you can imagine, the different ways in which you treat the edge effects will start showing differences, because that's when the edge effects are starting to matter. For very small distances, there isn't going to be much in terms of an edge effect. Since we know that the theoretical K function is pi d squared or pi h squared, depending on the notation you use, there is an alternative way to show this, and you, I think Krimstad does it this way, in that it subtracts pi d squared from the observed K measure. So if we go back to the previous slide, you see that you can take this blue line here and subtract it from here. The result is that the blue line will become horizontal, and these are the differences between the K function and the blue line. Okay, so this, again, same thing, same edge corrections. Still no inference. Okay. The inference we get from the randomization envelopes. Always the same idea: create random point patterns, recompute the K function, do this 999 times, then you get your maximum value and your minimum value under complete spatial randomness, and these give you your two envelopes. Complete spatial randomness is in the middle. We see for Cardiff, we're above in the K function, above is clustering, below is inhibition. So because we now know specifically what the function is for the complete spatial, the K function under complete spatial randomness, it's pi h squared or pi d squared, depending on what you use. So if K is above it, it's clustering. If K is below it, it's regular. So as before, with the G function, the F function, the J function, and the K function, the mechanics are always the same. And the lab on Thursday will be very simple, because if you've done it for the J function or the G function, it's the same thing. You just specify a different function, in this case the K function. So if we look to our three example patterns, the first one is the complete spatial randomness, random one, and we see that the black line is in fact in the envelope, tracks more or less the red line. Now, think about this for a second. Remember what I said about the precision of the estimate of the K function. What happens to that precision as the distance increases? It goes down. So in other words, the variance of the estimate goes up, which means that the actual number you get will vary more away from the true number that you should get. And just in an intuitive way, look at this graph, and you can get some sense. I mean, if you follow me, you can get some sense of what is going on here. See, in the early distances, the black line tracks the red line very closely. As we get into the higher distances, it gets further away from the red line. That's not because it is less spatially random. Could be, but in this case we control it, so we know that's not the case. But it is because the estimate that we get, the K, our average that we compute from the data, is less good of an estimate for the true K function. And this is a problem, and we'll deal with that problem in a minute. Okay. So as the distance increases, the quality of our K estimate goes down. It gets worse as an estimate of the true K function for our pattern. In this case, we're cheating because we know what the true function is. It's this red line, and we see that we're fine here, but as we get into the higher distances, we get further and further away from it, which is just a consequence of the randomness in our sample, if you wish, because we don't actually have the mean, we have an average, which is computed from the data. So there's sampling variance in that computation. This is what we're picking up. That sampling variance is not constant with distance. It goes up with distance. The second example is our clustered pattern, our Poisson cluster process. And here again, we see that we move above the envelope. As the distances get bigger, these curves can get more erratic because of the greater variance. And then the final example is the one with the inhibition process, where it's more regular, and in this case the K function is a little bit below, but not fully for the larger distances. The K function, and I won't elaborate on this because I want to give you some other aspects of the K function, but the K function can be turned into a formal significance test for complete spatial randomness. As I mentioned, this variance instability is a problem, so we might want to correct for that. The standard way to do this is a square root. In this case, it's pi h squared, so we get this pi in there as well. So we take the square root of this ratio, and that is referred to as the L function. And depending on the software, the L function is plotted against distance, or the difference, just like we did before. We had k minus pi d squared that we plotted against the distance. L minus h is plotted against distance, against h as well. And again, I'm pretty sure CrimeStat uses this option. So in the CrimeStat result, you will get a flat line as the reference, and then the difference between L and what the value would be under complete spatial randomness is the actual curve shown. So if we take the L function, that's this black one here, against distance, then because of the standardization, the complete spatial random curve is actually the diagonal. And then if we take the distance, so now we're going to take the difference between the black line and the red line, and that then becomes this type of function. All basically showing you the same thing. So these 4 different graphs all give you the same information. The original K function with its, parabolic complete spatial randomness reference, the difference between that function and pi d squared, then the square root of the original K function divided by pi, which is a rescaling, plotted against the distance, or the difference between that and h, which is this last one that we see here. There's no difference between these. These are just rescalings or different alternative presentations of the same result. So there's nothing different.